So good afternoon. Today our speaker is Goold, and let me briefly introduce him. So John got his PhD in 2009 in the University of Cork with Thomas Bush. He was working in quantum gases, and then he was a postdoc in Singapore. And then he got for several months, and then he got a Marie Curie fellowship, and he was working in Oxford for about 3 years, isn't it? And now he is working from August 2013 at the Institute of the International Center for Theoretical Physics, the ICTP in Trieste. He's been working in the last year in quantum thermodynamics with several interesting contributions, and today he will show us this work, steps towards experimental demonstration of information to energy conversion in a quantum system at the Landauer limit. Just last thing, John will be with us 1 month. He's visiting us during these months, so if anyone wants to have some time for discussion, please just come. Okay.
Yeah, so I guess first of all, thanks very much to Roberta for giving me the opportunity to visit this very nice island and this very nice institute. So yeah, I mean, Roberta also explained to me that the audience is quite general here at the institute. Many different topics are being studied. So I tried to make the talk in such a way that at least for 15 minutes nobody should fall asleep. Will be kind of a general, well, this is a challenge, a general history introduction to the subject. So I mean, what I'd like to say to you today is basically I'd like to tell you a little bit about some of the work I've been doing on the thermodynamics of quantum systems over the past couple of years. So, I mean, sometimes when you mention thermodynamics of quantum systems, people look at you a bit funny and they say, well, okay, I mean, this is an old topic, why not use quantum statistical mechanics? But actually, what I mean is that, I mean, I'm taking small systems where, generally speaking, the thermodynamic limit does not apply, so fluctuations about average values become important. And also some intrinsic quantum effects become important at that level. So I start the talk with a quote about why studying non-equilibrium physics in general is interesting. And there's this nice quote by Boltzmann, which says, "Available energy is the main object at stake in the struggle for existence and the evolution of the world." And this is something which not should just concern physicists, but concern everyone. I mean, we live our lives in a non-equilibrium way. We maintain our body temperature, even though the temperature outside varies. And of course, when you equilibrate, that this is a very sad day for your family. Okay? Actually, I moved 2 months ago to the small coastal village of Duino, which is about 20 kilometers up the coast from Trieste, and this is the view from my house. So actually, this house, which I see from my doorstep, is the house where Boltzmann himself equilibrated. Here is a picture of me and the granddaughter of Boltzmann. I met her in February of this year when they erected this plaque outside the door with the famous entropy function. Okay. Anyway, so why was Boltzmann so sad? Well, okay, there were many reasons, but one of the reasons is that his big contribution was before Maxwell and Boltzmann, I guess, thermodynamics was a purely phenomenological theory. It was invented purely for capitalistic reasons. So basically people wanted to make more money from producing more work out of heat, okay, and to abolish, let's say, employment. And the laws themselves were purely empirical, okay, and there was no real theoretic. And it was the work of first Maxwell and then Boltzmann which put it all on a firmer footing in the advent of statistical mechanics. So one of the things that Boltzmann, of course, worked on was this idea of irreversibility, okay? And he is sharing a famous set of letters with one of his collaborators who was Loschmidt, okay? And Loschmidt had a problem with his formulation of the second law. Loschmidt said, okay, if I take one of your gases, and if I can track all of the trajectories of the particles of the gas, reverse the sign of their momentum, then I go back to the initial condition. Then what does it mean that entropy always must increase? The laws of physics are invariant under such transformations, and that forced Boltzmann to revisit what he called his concept of irreversibility, and he introduced the so-called molecular chaos assumption into the second law. Okay? So many people call this the Loschmidt demon. Okay? And why demon? Well, actually, before Boltzmann started to think about irreversibility, that's when Maxwell was doing it. Okay? Maxwell has this famous book, which is his theory of heat, which was written a very long time ago now. Okay, but in this, you see this quote in the last chapter, which is problems of the second law, or second principle. He says, okay, not much. He says, if we conceive of a being whose faculties are so sharpened that he can follow every molecule in its course, such a being whose attributes are essentially finite as their own. You see, I love this because this shows how religious Maxwell was. Because he says, of course, if you wasn't like us, it could be God and he can do what he wants. Okay? So we'd be able to do what is present impossible for us without the expenditure of work. He could raise the temperature of B and lower that of A in contradiction to the second law of thermodynamics. So what you have to imagine is a box like this, okay? You have a gas, and you have this being on top, okay, with access to this shutter, okay? And every time he sees a fast particle coming by, he leaves it through, okay? So he basically creates this temperature gradient at the expense of no work because he's raising and lowering things. So this decreases the entropy of the system. So this being of Maxwell, which is now known as Maxwell's demon, was christened actually by someone who was born in Ireland, in the place of my birth, Kelvin. Okay, and you will see the original paper of Kelvin in Nature in 1874. Okay, where he has this beautiful paper called the Kinetic theory of the dissipation of energy, where again he's considering the irreversibility in dynamics. So if you read this paper, it's incredibly modern, even though it's 1874. It's really beautiful. He tells you about waterfalls going backwards, blah, blah, blah. And you see in a little footnote, he starts to quote Maxwell, and he says, the definition of a demon, according to the use of this word by Maxwell, is an intelligent being endowed with free will and fine enough tactile and perceptive organization to give him the faculty of observing and influencing individuals. Of course, at that time, irrespective of these problems they had with these microscopic origins of the second law, they basically believed that this was sort of academic. We couldn't know particles anyway, so there's no point in worrying about it. So the next step in the story came in the 30s. Okay, so everybody, of course, knows this guy, but hands up, who knows him? One person. It's always one person. It's amazing. No, because it's amazing because of this person's contribution to physics. Okay, so the guy's name is Leo Szilard. He's a Hungarian Jew. He patented the first nuclear reactor with Fermi. Okay, he was the first person to conceive of the fact that you could create a chain reaction in a nuclear bomb. Okay, he wrote the original letter to Roosevelt saying that we must start the Manhattan Project, and his work basically formed the basis of what we call now cybernetics. Well, where did he come in this picture? So he was thinking about Maxwell's demon in an ingenious way. Okay? So in this paper in German, you have what's now known as Szilard's engine. Okay? What was the brilliance of Szilard was that he reduced the Maxwell demon to a binary decision process. Okay? One particle in the gas, the demon slides a partition, then the crucial point is that the demon measures whether the particle is on the left or the right. And due to the information acquired by that measurement, he's able to basically put a pulley on and extract work by isothermal expansion. Okay, so exactly kBt log 2 of work. So this is the first real example of 1 bit of information in the history of physics. And if you take it in historical context, it's quite amazing, because this is 20 years prior to the Shannon's theory of information. Okay, so the interesting thing is that basically he didn't get it right. So what was the problem here? So the demon comes along, he slides in the partition, he gets his work out, he takes it back out again, he starts the whole thing again. He's created a perpetual motion machine of the second kind. So where's the catch? How do you reconcile this with second law? And Szilard, he believed that basically it was the process itself which would be the source of entropy production, which would balance this work extraction in order to say the second law. Okay? Von Neumann also believed that. And actually, basically, you see this quote: one may assume that a measurement procedure is fundamentally associated with a certain definitive average entropy production, and that this restores concordance with the second law. So Szilard, von Neumann, and then some other big guys basically all thought that this was due to the measurement process, so the act of acquiring the information. This was what gives you the kBt log 2 of entropy production. And if you look in the literature, there's these works of Brillouin, Demer, and Gabor. Okay, so basically what they thought was that they constructed basically one model, okay, which linked the detection process to entropy production. So they actually computed, if they use photons to scatter off a particle in the gas, then they were able to show that this had entropy production, and basically, okay, they said this is it. This is the exorcism of the demon. Okay. There was many philosophical criticisms, because of course this is really observer-dependent definitions are unacceptable, etc. But it more or less lay dormant, okay, for 20 more years. It was thought to be done. And then came computation, okay? So you had the Turing machine, you had the advent of universal computation, theory of universal computation, Shannon's theory. And at the time in IBM, a guy called Ralph Landauer, right, was again considering what is the thermodynamic cost for doing computations. And what he did was he basically set up a model, which was essentially just a simple Langevin-like model of a one particle in a double well. And he showed that in fact you could perform the measurement in a reversible way. It was possible by mapping it to another system and so on. And what he showed was that in fact what is the irreversible part of this whole procedure was the erasure of the information. So you have to model the demon as having a 1-bit memory. So when he measures left or right, stores that information, and then it's the wiping of the information, the reset to 1, okay, which actually leads to the kBt log 2 of entropy production. So he identified a class of logically irreversible operations which always led to an entropy production. Okay, so an example is I take some ticker tape 100111 and I set everything to 1. That's a logically irreversible operation. It doesn't have an inverse. Okay, so in this type of operation you have entropy production. And this then led to Charlie Bennett, also of IBM, to construct this theory of reversible computation. And then everyone said, okay, that's great. Maxwell's demon is explained by the fact that the demon has a memory, the memory needs to be erased, that closes the cycle, everything is done. And that's the general consensus today. So the very pragmatic thing about Landauer and Landauer's principle, which says the heat dissipated to the bath in any logically irreversible computation is always basically greater than the information theoretic entropy change. Okay? It's extremely pragmatic because, I mean, if you really want to set up circuits, etc., you have to care about where heat goes. You have to care about the amount of heat you're creating by your circuit. Okay? And you can see this quote I get from Nano Letters, where, I mean, energy dissipation per logic operation, present-day silicon-based digital circuits, about a factor of 1,000 greater than the ultimate Landauer limit, but it's predicted to quickly attain it within the next couple of decades. And of course, if you work in quantum information, you realize also there's the theory of quantum computation, and how would you measure, I mean, how would you construct or analyze the heat dissipated by information processing and such things, okay? Right, so if you want to read more about this history and the original papers, you can find most of the stuff up to 2003 in this book. And if you want to see many of the quantum extensions, you can check this review of modern physics by Vladko, Franco Nori, and Franco Nori's student, which is this physics of Maxwell demon information. So up to about say 4 years ago, that's the story. Okay, so what's the story today? The story today is that these thought experiments of Szilard and the fundamental Landauer ratio experiments at a single bit level, we're now at a stage where even classically in the lab we can actually analyze these type of things, these thought experiments. Okay, there's a series of works which are, let's say, the newest things are experiments, okay, whereby they can really measure this kBt log 2 of heat, okay, dissipated to the environment at that limit, at the lowest limit. So I focus on this work here because I like it. So they set up basically a bit, okay, which is just some optical potential with a microsphere, okay. Left and right, the wells are 1 and 0, they're your logical states, okay. It's surrounded by solution. And all they do basically is a manipulation of the well such that whether you start off on the left or the right, you always end in the right, okay. This is a reset 1. What they were able to do in this thing was basically very accurately measure the average heat, okay, given off by this computation, basic computation, and they show if they make the manipulation of the well slow enough, they can basically approach this kBt log 2 limit, which was predicted by Landauer, okay. Now, what all of these experiments at this limit have in common, okay, and which is something that we have to deal with, is the fact that at this single particle level, your physics is completely dominated by fluctuations about average value. You don't get standard thermodynamics, so you have to use a different formalism of thermodynamics, something which, let's say, is known as stochastic thermodynamics, which is very well by now formulated for classical systems, but for quantum systems there are many problems, and I'll talk about some of them now. Okay, so moving on. So my own research basically is about taking these ideas coming from the community of people studying the non-equilibrium statistical physics and looking to see if I can explore and generalize the concepts in systems which are familiar from quantum optics, quantum gases, nanomechanical oscillators, etc. Okay, so the first thing I guess we should do is we should define what work and heat are. So the first law of thermodynamics says the change in energy, okay, is equal to the change in heat plus the change in work. Okay, so what are heat and work? So if you take the classical approach, what you do is you have some ensemble, okay, say the canonical ensemble, and now you change the Hamiltonian, okay, while it's connected to some bath, okay, some heat bath. Then the change in probabilities of the state at fixed Hamiltonian you can attribute to being heat, okay, whereas the change of energies at fixed probabilities you associate to being work, okay, and this holds for this quasi-static transformation. Okay, it's textbook stuff. Suppose now you wanted to relax this quasi-static transformation that you weren't always assuming to be in state with your bath, which is actually the real situation for small systems. One approach you could take is you could try and formulate the dynamics of the ensemble using, let's say, for instance, a master equation. Okay, so with a master equation, typically, I mean, there's extensions. Typically, you assume weak coupling with the bath, maybe Markov conditions, depending on how good you are. And basically, you do the same procedure as what's shown in the book of Schrödinger, and you separate out now the change of the density matrix and the change of the Hamiltonian. You integrate over the time scale of your procedure. Okay? And this is nicely done in this paper by IFISC in the late 70s. Okay, but sometimes you're not actually... you're not given the luxury of knowing your state at all times, okay? You might only know the energy of your state initially and the energy of your state after the process, okay? Which is typically what you have in an experiment. You have an input and an output, and then you have to try and calculate what went on in between, and it's not very easy. So let me focus first on work, okay? Let me focus on the situation where I don't have any heat, okay? If I don't have any heat in a quantum mechanical process, then I'm purely unitary. Okay, I can start in equilibrium, then I take the system out of equilibrium by doing a unitary transformation on the state. Okay? So you know if you're unitary, you can just manipulate the equation, you'll find that the heat term is 0. So all of the change in energy is solely attributed to the work. And what you have to be very careful about now is you have to say, okay, I'm dealing with a small system, it's the average work is equal to the internal energy change. So the work itself will fluctuate, okay? If you do an experiment many times, you'll get different values for W, you'll get a distribution for W, and the average, the first moment of that distribution is now what conforms to the first law and second law of thermodynamics. So now we get start getting a little bit more technical. So I say that the work is described by a probability distribution. Okay, so I start in thermal equilibrium in a Gibbs state. Okay, and now what I have to assume is that I'm going to do a unitary protocol, which basically in the lab say is some laser described by parameter lambda of t. Okay, some control, which generates a family of unitary operators, which are parameterized by lambda. Now, what I want to say is that I need to measure the system twice to characterize the work. I need to measure the energy before I do the unitary and then measure the system after I do unitary. So what I do is I say, okay, I project onto the energy eigenbasis of the system initially, and I get some outcome, En, with probability Pn, given by the Boltzmann weight. Then I basically do my work, I do my unitary evolution, and I measure the energy again. Now my second energy measurement, okay, is conditioned on the outcome of the first. Okay, so I have some conditional probability Pmn. So basically I prepare a state, I measure its energy, I evolve it by the unitary operator, I measure it again, and then I build the full statistics of the work. Okay? And it looks like this. Okay? So basically what we have is we have transitions. Okay, of course. I take a system out of equilibrium, you form coherences in the energy eigenbasis. Okay, and my transitions, probabilities are these conditional probabilities. Okay? My distribution itself is a series of peaks now at the difference in energies between the two Hamiltonian configurations, Hi and Hf. Suppose I was at zero temperature. This is somehow easy, makes it easy to understand. Suppose I was at zero temperature and I prepared the ground state here. Okay? I prepare the ground state here and then I do an adiabatic transformation on the state. So I do really slowly. What would I expect here? Well, I would expect simply a single delta peak at the energy difference between here and here. Okay? But when I go out of equilibrium, then I get many peaks. I get a whole spectrum of energy differences. And now the first moment of this distribution here is the average work done over many experimental runs. Okay? Is this clear? Because if it's not clear, then we shouldn't go on. Okay, good. So why is it interesting to study this distribution of work? Okay, so one of the things that's interesting to study about this distribution of work is that it's found quite recently over the past 15 years that the distribution itself obeys incredible symmetry relations. Okay, so maybe people here who may be working in condensed matter physics, linear response theory is sort of a typical example of what's called a fluctuation dissipation relation. Okay, so you maybe probe a system, you want to learn about a correlation function, of equilibrium correlation function, and there are results which hold in the linear response in order for to do that. But if you study P of W, what you can get is you can get fluctuation dissipation relations, which are essentially the full nonlinear response to the problem. Okay, by studying carefully fluctuations in P of W, I can extract information about an equilibrium property, irrespective of how far from equilibrium I take the system. So one of the most famous ones is the so-called Asaki-Crooks relation, and what it is, very, let's say quickly, is that if I do two different experiments, okay, I do the first experiment, I can imagine, okay, a piston with a small gas in it, but it could be a harmonic trap whereby you change the frequency, could be whatever, it could be two levels of a squid and you manipulate them. But imagine the piston, I start in equilibrium, the gas is in equilibrium, and then I just violently push the piston in, okay? And I don't wait for it to equilibrate, but I measure the work, okay? In the way that I've told you with this distribution. Fine, and I build my statistics. Now I consider essentially a reverse process, where I start now in here at equilibrium, and I pull it out in the same way, using the mirror reverse trajectory, okay? If I take those two distributions that I've got from the two different experiments, and I divide them by each other, I can extract the free energy difference in equilibrium between the configurations at the beginning and at the end. Okay, which is quite remarkable, because the free energy difference is the work done as if you had been isothermal. So irrespective of how far from equilibrium I take my system, provided I can do this backwards experiment, I can always extract the free energy difference, the equilibrium free energy difference, and the initial temperature. Okay? So a corollary of this thing is this probably more famous equality, which is the Dzerzhinsky equality, and it's basically what these fluctuation relations are essentially very refined statements of second law of thermodynamics, which are applicable to nanoscale systems where fluctuations are very large. Okay? And you can read more about them, the quantum variance, in two papers. One which is, I would say, more at an introductory level by Campisi, Peter Hangi, this group. And the other one is by Esposito and Mukamel, which is more basically suitable for people who've studied the full counting statistics before, which is very similar in the kind of mindset as this. Okay, so what sort of stuff can you also learn about from this work distribution? Well, the first moment, okay, the average work done, if you actually subtract the free energy difference, the equilibrium free energy difference of the virtual process from that, what you get is you get all of the excess energy you've pumped into your system by being out of equilibrium. Okay, so this would be zero if I did an isothermal process because the average work would be delta F. Okay. Now this actually appears quite naturally from the Crooks relation. So look, I mean, if I take the right hand side, okay, which is the W minus delta F. Now imagine taking the log of both sides, the exponential goes away. And now I integrate both sides over Pf of W, okay? Then I get beta W minus delta F, okay, which is the excess or dissipated work, is equal to this quantity. And this quantity is well known in information theory as the Kullback-Leiber divergence. So what it is it's the relative entropy between two distributions. Operationally speaking, it measures how different they are from each other. So if you do a completely reversible equilibrium transformation, there will be no difference between your forward and backward distribution. In other words, you'll have no way of knowing whether you saw a movie running in one way or running in the other. And that's the essence of breaking the symmetry, which is related to the irreversibility, and hence the emergent arrow of time in the sense of the second law. Okay? So you can show then that this quantity is always positive because the relative entropy is always positive. Okay, so let's skip this bit. So now about experiments, okay? So if you wanted to look, at least because these things are quite new, they've been formulated over the last 15 years or so. If you wanted to explore them in the lab to show that you can, well, to demonstrate control and also to show that they actually, they're there as they should be, and you'd like to study the thermal system, then you need to suggest experiments. So the first experiment in the quantum domain, okay, that's been suggested is in the ion trapping group of Ferdinand Schmidt-Kahler around 2008. And they had a very simple but quite elegant proposal that they would just take the harmonic oscillator, they prepare an equilibrium state, a single calcium ion, and then they just do basically a squeezing of the trap potential. Now, the difficulty here is that it seems like a very simple thing to do, but the difficulty for an experimentalist is the following. You have to prepare a thermal state, which is okay, but the problem is that you have to project, you have to measure energy, not once but twice, and in between do a process, a controlled process. So we know that's extremely difficult to do because typically measurements in quantum mechanics will destroy your system, okay? Or at least most of the time, unless you're extremely clever. They proposed a workaround, but unfortunately they never carried out the experiment because it was just beyond what they had in the lab, but they suggested that people with better equipment at that time could do it. So this is where we came in. The first contribution, let's say, that we gave for this topic was to suggest a way to measure this distribution in a quantum system, okay? So, as I said, these guys basically went to directly measure out the work statistics by kind of tomography of the state. But actually, if you take this distribution and you Fourier transform it, what you find is that you find its characteristic function, in fact, has a physical meaning, and I'll explain that now. So if you look at what happens when you Fourier transform this, just trust me on the mathematics, is basically you find something which looks like a 2-point in time correlation function. Okay? So what we suggested was to measure this. Okay? And now how would you do that? So this is something which is probably the most technical part of the talk, so bear with me. There's a way that you can extract functions like this using something known as phase estimation in the theory of let's say quantum information, quantum optics. So this was a jointly submitted work. Mauro Paternostro's group in Belfast, and also the group I was in, Vlatko Vedral in Oxford, in collaboration with Sarah Fazio's group and Stephen Clark and Dieter Yash's group. So what we proposed is that if you introduce an ancillary system, so I have this, just look at this system here. So this one here is a thermal state of, imagine the ion trap in the last slide. What I do is I introduce an ancillary system, so another system into the picture, which just takes part as a spectator. I apply this operation between these two guys, which is the Hadamard gate. It brings this qubit into a superposition, and then I do what are known as control operations on the ancilla. So what these do, it's like an interferometer. I've made a superposition of up and down in the qubit, and now, depending whether the qubit's down, I do something, and whether it's up, I do another thing. This is the interferometer, and then basically I put another Hadamard operation, and I measure the sigma x and sigma y components of the qubit. Okay? It turns out that if you do this with an ion trap, so I mean, for instance, you could imagine this qubit, the ancillary guy is the internal degrees of freedom of the ion, whereas the system itself is the external vibrational degree of freedom, and you couple them by a standard Rabi-like term, which you have control over these guys with the lasers in your lab. You could actually implement this circuit. So we tested the protocol. It's protocol specific. You can do whatever you want, but this is just an example. I don't want to dwell too much on it because it's technical. But in the end, what I wanted to show you is that when you measure, okay, when you do your measurements here on your qubit, what actually you get is these are the four terms, up, up, down, down of the ancilla, and in front of them are four time-dependent terms. Okay, two dephasing terms, two on the on-diagonals. And these terms actually encode the real and imaginary part of the work done on your oscillator during the Unitary Protocol. Okay? So I basically mapped the problem of calculating the work done in some process onto the on and off diagonal parts of an ancilla. And this is known as phase estimation. It's extremely powerful, and it can be done. So what we did in the paper was just to make sure that everything was okay. We added noise, we added a lot of stuff, and basically we said, okay, this is a way you can get the work statistics out in a given problem, okay, without having to resort to this really restrictive way of making projective measurements onto the state, okay, which is very destructive. And then,
sorry, John, here the dynamics of the system was unitary.
Okay, exactly. This is a good point. So so it's a tricky point. Indeed, we are not interested in the work done on the ancilla plus the system. The point is that the manipulations on the vibrational degree of freedom essentially mimic a unitary operation on the vibrational degree of freedom. Like, you know yourself, if you have a two-level system coupled to the mode, manipulations on the two-level system lead to conditional displacements on the vibrational degree of freedom, and we're interested in those conditional displacements as the actual work. Okay, so it's not the full work done on the whole lot. It's just the work done by the conditional displacements on the vibrational degree of freedom. It's a technical point, but fair point. Okay, so 1 year later, the experiment was done. Okay, the experiment was done in a different system. We proposed for ion traps, but the guys in Rio de Janeiro, okay, I can tell you something about Rio de Janeiro, that even though the subject of this experiment is studying work, it's an extremely difficult place to do any. You can see the location of the institute, but basically what they did. Okay, so what they did in this experiment is a slight modification of the scheme, in the sense that now they don't have a vibrational degree of freedom. They had two qubits, one which is the ancilla and one which is something you want to do work on. Okay, so basically what they do is they have a chloroform molecule, okay, and they do work on the C nucleus, okay, by just putting in an RF field, and this RF field basically has the property which just raises and lowers the levels of the nuclear spin, okay. And in the meantime, while they're doing this RF field on the C, they do this phase estimation protocol on the H nucleus, okay. exactly the same way as I said in the talk. So we choose a linear ramp, okay? It's done in a highly non-equilibrium way. And in the end, what you get is, okay, first of all, I should say that not only can you push the two levels in, you can also pull them apart by a different pulse, okay? And at different speeds, etc. And what you do is you simply just measure, as we said, the ancillary qubit. You construct the characteristic function from its dephasing. And then what you get is essentially you get the peaks of what the work distribution should be. So these are at different temperatures, at different speeds. But I should say that basically there are 4 peaks. There are 4 peaks because there's 4 possible combinations of transitions. You have a 2-level system. It can go to 0 to 1, 0 to 0, or 1 to 0, or 1 to 1. Okay, so these are what these peaks mean. You see at finite temperature you're getting this sort of Gaussian distribution, as you should, as large temperatures. Yeah, so the basic message of this type of thing, which is important for what I'm going to say next, is that work distributions can be basically constructed via the phasing of an ancillary system, dephasing of an ancillary system. Okay, so there's forward, backward distribution, and this here is on a logarithmic scale is the Crooks relation, okay, verified for the first time in a quantum system. Okay, it was experimental collaboration with the guys in Rio de Janeiro. So what is quite nice about this is that you see different temperatures here. You see, irrespective of the rate of the pushing or pulling of the qubit, you always get intersection at the free energy difference as basically as expected by the Crooks relation. Also, you can extract the initial temperature, and we propose as well that this could in principle be modified to do thermometry systems. Okay, so probably for now it's not really developed, but you can measure both delta F and beta. Okay. So what I want to talk about now is heat. Okay. I talked about work, and now I talk about heat. And I'm going to talk about situations where you have heat, but you don't do work. Okay? Now this is a trickier situation, because basically you don't have this luxury of unitary dynamics anymore. You have connection with a bath, and typically your dynamics is non-unitary. So going back again to this picture, which was motivated from Lischke's paper, the heat, remember again, is basically the change of the density matrix, or the change of the state at fixed Hamiltonian. Okay? And in fact, what you can do is you can formulate a nice, basically a nice statement of the Landauer Principle. Okay, so Landauer Principle says that, if you remember from the start of the talk, that the heat dissipated in an elementary computational algorithm is essentially greater than the information theoretical entropy change, okay, of the state. So imagine you have a system and a reservoir, okay, both described by Hilbert spaces. The reservoir is initially in a thermal state, temperature. The system S and the reservoir are initially uncorrelated as an assumption. The system doesn't have to be thermal, it can be whatever you want. And then you do a unitary operation, or a computation, whatever you want to call it, okay? And when you go through this, you define the entropy change of the system, you define the average heat change in the reservoir, just as the trace of H over the reservoir at the end, minus the trace of H rho R. When you do all of this, basically what you can derive is you can derive that the first moment of the heat distribution, or the average heat, is equal to the von Neumann change of the system, plus the mutual information between the system and the reservoir, which measures how strongly correlated they are at the end of the protocol, plus the entropy between the reservoir initially. So let me just explain these terms. Suppose I did a transformation which took me from an equilibrium state to an equilibrium state. Okay? In that case, I'm back at equilibrium thermodynamics, right? Then the change in the entropy should be the heat. Okay? These terms go away because you have no correlations at the end, and the bath remains the same. So if you go through either of these two works, they'll go into more detail of why this is a nice derivation of what Landauer's principle is. Okay? Now, what we want to do, the idea that we had was, we are going to construct the heat distribution on this process, okay? And from that, we're going to measure out the distribution, and see if we can do something that hasn't been done before experimentally, which is to measure the heat dissipated by a logical, by a computational process at the limit of Landauer. Okay? It has not been done before in a quantum system. So it's more technical. Bear with me. I basically now measure just on the reservoir. I do the global unitary, which acts on the system and the reservoir, but I only measure the dissipation of the reservoir. So I project onto the energy eigenbasis of the reservoir. I evolve non-unitarily. Then I measure again onto the energy eigenbasis of the reservoir, and I construct the distribution of energy changes. Okay. Now, operationally speaking, this is a map from states to states. And you look at the first moment of this distribution, you find, as you should expect, that the first moment is simply just the average energy change in the bath. Okay? Which is good. It should be. If it's not, then you're in trouble. This formalism doesn't work. Okay, so now what you do is you do exactly the same as I said for work. You Fourier transform it. Okay, you find this characteristic function, which is a little bit different. And you construct a circuit diagram, okay, with an ancilla in order for you to read out this characteristic function of now the heat distribution. So prepare an ancilla, some reservoir, some system. Of course, you have to do controlled operations on a reservoir, okay? And now this is a bit funny for somebody coming from traditional. Reservoir is typically something you don't have any control over. In our case, it's some finite dimensional quantum system. It has to be. So we do a controlled operation. So I start the interferometry. I do unitary process, which couples the system and the reservoir. I do again another controlled operation. I measure out the ancilla. And again, if you go through the steps of this interferometer, at the end, when you trace out the reservoir and the system, you just look at the ancilla. What you get is on the off-diagonal terms this time, is you get the real and imaginary parts of the characteristic function of the heat dissipated into the reservoir. Okay? So again, I'm sorry for the technicality, but I mean, some people are probably interested. But the basic idea is that you can construct the full distribution of heat dissipated into the reservoir via coupling in an ancilla qubit and doing phase estimation on it. And the reason why this is important for a long time, as far as I can see in the literature, is that people are always focusing on measuring energy directly. Okay, we're bypassing the need to actually make projective measurements onto the reservoir. Okay, so this is actually work which is being done in Rio, in the liquid state NMR laboratory there, but it's not published. This is just results I was discussing the other morning with collaborators. So here we were actually, again, able to implement this circuit on a fluorine ensemble. And I can show you something quite nice. The following is very, in my opinion, I'm quite happy with it. Okay, it's not perfect, but what these use are just random unitary operations. Okay, they're just something that the experimentalists make up. Okay, computation, NOT gates, etc. Okay, here is the theoretical curve, which is delta H. Okay, and these are the heat, the average heat we're measuring from our technique. So we're almost at this Landauer limit. Okay, we won't ever be at it because we know that there's this entropy production described by the mutual information plus the relative entropy. So things are looking good. I mean, we're basically now saying that we can measure the heat dissipated by the most primitive of quantum logic gates. Okay? And, okay, I think this is important because if we really believe that computation is going to reach these small quantum systems, then we have to be very, very careful over which operations gates we're applying, because otherwise you melt your circuit board if you're too high in this curve. Okay, so people have not been able to measure the heat dissipated in these circuits at this limit before. Okay, and this is my contribution. Okay, so this work, the other two theorists involved in this is Kevin Modi, who just recently became a permanent member of staff at Monash in university, and Lucas Celery in the University of Goiás in Brazil. How much time do I have? 5 minutes. Okay, let me skip this because it's technical. It's probably not interesting to many people. Just let me conclude with this. So, what's quite interesting for me as a theorist is that the second law is somehow as old as thermodynamics. But if you study it, and you study it in different systems, it's a continual inspiration for new physics, okay? And it's something I've learned in the last 2 years while studying it myself. I like this quote by Eddington, which says, "The law that entropy always increases holds, I think, the supreme position amongst the laws of nature. If someone points out that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it's found to be contradicted by observation, well, experimentalists, they screw things up sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. Nothing for it to collapse into the deepest humiliation." And with that, I thank you.
Thank you, John. There is time for some questions or comments.
Yeah.
Emilio?
You have mentioned at least twice that you access real and imaginary parts of
No.
lifetimes.
No, I understand. Okay, so yeah, I think maybe I made a mistake myself in the way I said it, but okay. This one is best to see it. I didn't say the energy, the Fourier transform of the distributions. Okay, the Fourier transform of the distribution itself has real and imaginary parts. I mean, if you expand it, basically you get just this, because this is delta functions. Okay, this is essentially just a sum of plane waves which have real and imaginary parts. And I'm saying that the real and imaginary part of this function are mapped out in the code. Sorry if it was confusing. Yeah.
So I have some concerns about the way you define heat and the work. Because actually, it's kind of motivated by the first law of thermodynamics.
I'll go back to the work. Okay. So actually, you're right to be concerned in the sense that for a long time. Okay. So the issue is the following. The usual way to describe the work, okay, statistical mechanics, is the free energy difference, okay, between the initial equilibrium state and the final equilibrium state. Here you always start in equilibrium, whether you're classical or you're quantum, but you drive the system in a non-equilibrium way, so that your final state is not an equilibrium state, okay? And this gets rid of the free energy difference. Idea of measuring with the free energy difference. So what do you do? So basically people thought for a while that you could maybe construct a Hermitian operator which would describe the work, so the difference of the Hamiltonians, and then you value with the initial state. But actually what you realize there is that this work can't be observable in the quantum sense because it's a process dependent, a path dependent quantity, and in the quantum mechanical sense it requires two measurements, so it must be related to a correlation function of some sort. I mean, the inverse Fourier transform of the distribution itself. This is the idea of Peter Hange and Eric Lutz and other people from the statistical mechanics community, where they have this, I don't know, short paper where they say work is not unobservable and must be described by distribution. It's the general, say, consensus amongst this community. I would say there are still controversies, and I think it's fair enough. People say that maybe this isn't the best way to describe work in heat, in the sense that also it's very restrictive. It's very restrictive in the sense that you're restricted to initially preparing a canonical state. So you can't deal with general states, whereas people in quantum information would like to be able to generalize the work concept to arbitrary initial states. But
in your case, you split the energy. So quantum systems only know about energies.
Yes.
And then you split your energy into heat and work. And this splitting, in general, is not unique?
Yes. Okay, so good point.
Yes.
Yes.
I can take a little piece of your work definition and put it into the heat.
Yeah. No, you're right. And the problem isn't work, actually. The problem is always heat. It's a subtle point, and it's a good point that you raise, because suppose I don't have a bath. Then I don't have to worry about heat. I don't have anything. Everything I do is work, and that's clear, I think. The problem is when you have work and heat at the same time. Then it's very difficult to differentiate what's coming from dissipation due to the time-dependent nature of your process and the actual exchange with the bath. And I think that we get around it the way we set up the problem for the heat, because actually we are in a situation where we don't do work. So in the case where heat and work are basically going on at the same time, I don't think there's a clear consensus how to separate out those two contributions to the energy change at the moment, at least without some restrict assumptions like weak coupling, Markovian dynamics, and then maybe you can do this type of manipulation carefully. But if you, I think it's not known what goes on in full generality for quantum systems.
This, let's say, definition is arbitrary?
I would say that this definition by Elišky works for systems which are described by master equation. So under weak coupling conditions, etc. Yeah. Yeah.
So your method in order to obtain statistics of heat is also valid for any other observable of the bath?
Yes. Yes. No. Okay. So let me think about what you say. So, okay. So what you're saying, if I wanted to extract, no, because it's not. It's subtle, because unless you can tell me different, but here I have a difference of energy. So this is like a difference of Hamiltonians. So what you're saying, it's like you want to measure a single observable, whereas this is sort of the difference.
Yeah, but you can start in a different initial state.
Yeah, yeah. Actually, well, what you can definitely do is you can use these type of protocols, which are where I guess some of the inspiration for this type of thing is that people showed in quantum information that you can use this phase estimation algorithm to calculate the trace of the Hamiltonian unitary of the BAT, the DQC1. It's the single qubit computation models. So you can certainly get spectral information on the bath. I'm not so sure can you measure arbitrary observables. You can measure the probability distribution of differences of observables, I would say, with this, the way I set it up. With differences, sure, sure. The change of arbitrary observable, I agree, but not single observable.
And also for the entropy change in the bath.
Yes, yeah. But I have some issues with this, not that I have issues, but let's say I don't understand very well. There's also, there's a families of fluctuation relations, not just work fluctuation relations, but you can have fluctuation relations on any stochastic quantity. Okay, you can have fluctuations on the entropy, the heat, the work. Okay, and the problem with the entropic fluctuation relation for the quantum system is, the work and the heat are nice because you can think about measuring some observable, as you say, at two different times. Okay, so whereas the entropy itself, you have to measure somehow the state, the fluctuations in the state. So I don't see how you can do that without doing a tomography.
You have to measure in the eigenvalues of the actual state.
Yeah, but this is difficult for them, no? To measure in the. No, I think in principle, if you can do that, for sure you can measure this entropic fluctuation relations or distribution of entropy. The thing is that I think experimentalists, making measurements into the actual state basis, I don't know of any experiment in quantum mechanics where they actually can, unless they do tomography. Okay, time-dependent tomography, which is difficult. Probably they can do it for cavity QED, maybe something. I'm not sure. That's no point.
And why you focus on the heat?
Because okay. The obvious thing to say is because you can, but no. The reason is in fact the heat itself. We see that the first moment is actually very interesting. It's connected to this Landauer principle, right?
Yeah, but also the entropy of this is derived from the entropy change in the bath.
Yeah, but the thing is that I can infer information on this, right? So this part here is this irreversible entropic change.
But if you take the last term,
yeah.
and the heat,
yeah,
this is the entropy of the bath, the one normal entropy change of the bath.
Yes, that's correct. Yeah. So, but the thing is that, I mean, the elegant thing about this experiment or this proposal is that you can actually infer these entropic quantities just by looking at the heat. So that's the way we set it up, at least. But you're right. I mean, in principle, you can measure the entropy of the bath, infer it from your data.
Because maybe you can imagine another process of erasure of information, which is not only related to a flux of heat, but to another equilibrium process.
Yeah, no, it's a good point. I think we can discuss.
Further questions or comments? No? So let's thank John again.
It's a bit technical, but I have to do something else.
The second part I
It's
have
technical. Yeah, no, but it's... Oh, thank you.
I think